Hi, in this video, we're going to cover Chapter 1.5, Part 1, Exponential Functions. So what is an exponential function? It would have a basic form of, there's another typo here, a basic form of f of x equal to b to the x. B is base. B has to be positive, and then it cannot be 1, otherwise it's just a constant function. So what are the forms of these exponential functions, b to the x? Does it has a vertex? Does it has a constant slope? No. It's actually two particular form. So one like this, when b is greater than 1. So because if you just say, for example, if I have x and y to graph it, you make a table of 0, negative 1, 1, that should be sufficient. And then b to the y is, say, b to the x. Anything to the 0 is 1, right? B to the 1 is just b, a number, and b to the negative 1 is 1 over b. So you would graph 3 points here. 0, 1 is always in the y-intercept, and then the first point is 1, comma b, the base, and then the point on the left side of 0, comma 1 is negative 1, comma 1 over b. So this is like growth function. Now, if b is less than 1, you would have the similar table, but then because b is actually less than 1, so your graph would look like this. Okay, so there is actually two types of graph. One that goes from close to 0 on the left-hand side and then rise up, starting from mid the y-axis at 0, 1, and then rise up exponentially. The other one is rise up very exponentially on the negative side and then drop down through 0, 1 to close to 0. So when the base is a fraction less than 1, like 1/2, 1/4, you see that the graph go like this. So it's like a decay graph. And when b is a positive number that is greater than 1, then it goes exponentially. So that's how we graph the exponential function. It is used to model a lot of exponential growth or decay kind of applications. The domain of this function is all real number because you can plug in anything to the exponent of a number. The range for the basic one is always greater than 0. It would not drop below 0. It's always greater than 0. It would not reach 0. So there is a horizontal asymptote of y equal to 0. And the y-intercept is always 0, 1 because b to the 0 is always 1. So to use this function, we have to review some exponential law, which is if you multiply two numbers with the same base, you add the exponent. If you divide them, you subtract the exponent. If you have a power of an exponent, you multiply the exponent. And then we also have a definition of a negative exponent being the reciprocal, and a rational exponent of a over b is a root function of b to the power of x over a, to the power a. So these are the basic things that you should learn, and we have some, example here to practice exponent law or exponent properties. Before we go into that, I want to introduce a special base called e. So e is not a variable. It's a constant, just like pi, which is irrational. And how do you get e? E is when you add 1 to a very big number, 1 over a very big number, and then to the power of the same big number, then it will become e. So it's called an exponential constant. In your calculator, you'll see e also. And e as a base can be used to model natural change. So we call this a natural exponential constant, natural change. Okay, so e, if you look at the calculator, is around 2.7. Okay, so it is between 2 and 3. Another property of e is if you graph e to the x, because it's greater than, e is around this, right? Because it's greater than 1, so it should have this kind of shapes. And the special thing about this is at the y-intercept. So the slope is the y value is 1. The slope of the graph is also 1. So the graph of the slope and the y value are the same. Okay, so let's practice some exponent law. This calls for 125 to the power of negative 2 over 3. So let's take care of the negative first. Negative means exponent. Oh, no, negative means reciprocal. 1 over 125 2 over 3. And then we take care of this root. What is the root? The root is the denominator of the rational exponent. So it'll be 1 over cube root of 125. Now, normally we would write the square here, but you can also write the square outside because it's easier to do a cube root of a smaller number. So what is the cube root of 125? That is 5. So that means 5 squared. So whatever that is on the numerator, you delete it until later, after you take the root. So it's 1 over 25. And notice it's not a negative number. The negative exponent does not imply you have a negative number. Okay, B, let's use this power rule to simplify the power first. So this becomes 2, x to the 2/3 times 3 is 2. And then at the bottom, you multiply 2 in all of these. So you would have 4 squared x to the negative 2/3, right? 2 times negative 1/3 is negative 2/3. Now you would have 2 over 16. Simplify 2 and 16 as a fraction. And also x would be 2 minus negative 2 over 3. So this becomes 8 at the denominator. You can cancel this. Then the top would be x 2 plus 2 over 3. What is 2 plus 2 over 3? Is 6 over 3 plus 2 over 3 will be 8 over 3. Will be 8. Okay, so you can simplify it this way. This is another exponential expression that involves two variables. So we have a power of the product. So what we do is we square both of them. So it becomes x to the 6, y to the negative 2 over, we multiply this x power rule over here, x to the negative 2, y to the 2 times negative 2 is negative 4. And then it becomes x 6 minus negative 2 because we're dividing, so we have to minus it, times y, the top is negative 2, minus negative 4. So it turns out it becomes x to the 8, right? Minus and the minus is a positive. Y to the negative 2 plus 4 will be squared. So that's the answer for this. So we have introduced some growth function, the general growth function and general decay function that is used to model applications. Now the basic function is y b to the x, but to use it to model real life, we use a, b, t. T for time, okay, T for time. So if b is greater than 1, then it is a growth function, just like what we saw on the graphic. A is when time initial value. When time is 0, you would have A. So this is one form of the growth function. The other form is using the base e. So we would write it as a e to the kt, where k is positive. For decay function, we can also write it as abt, but b would be a less than 1 is a fraction. Of course, this has to be all greater than 0. So it's a fraction. B is a fraction. And then A is the value when time is 0. And then we can also do a natural decay function where we write it as a e to the kt. K is a negative number. So if you want to do a decay function, you can still use e, but you would have an exponent of negative. Let's do an example of using those growth and decay function. So this is for growing. Money is invested in an account. The annual growth rate is 2.5%. 2.5 change into decimal is 0.025, right? You move two places back, so you have 0.025. Write the formula for A of t, because see, look at, we do compound continuously. That is natural exponential growth. We would use E. Okay, E to do it. So A of t would be equal to A0, which is 500 that we have. And then E to the, because this is money for growing interest, so it'll be 0.025, the growth rate, t. Find the amount up after 15 years. So what you do is you would do A of 15 would equal to 500, E to the 0.025 times 15. So let's use our calculator. Turn it on. 500 times, where's our E? E is here, E to the power 0.025 times 15, all in the exponent. Okay, so this would give us the final amount of 727.4950. Okay. What was it? I forgot. 727.50. So you would say equal to 747.50. Okay, so that's how you do a growth function. The next things we want to do is graphing. Okay, let's see how we graph a basic exponential function. So we know we start from our basic one, right? So let's do my pencil first. Get the pencil. Okay, so our parent function is y equal to 2 to the x, right? But this is what? This is negative 2x minus 1. So the transformation is a reflection. Reflection and also a shift to the right, right? You have x minus 1. So to do this, we would do a table. Because it's shift to the right, so we would start from 1 instead of 0. 0 and 2. So what happened is when you pick your number, you pick the one where you have this being 0, 2 to the 0. So 2 to the 0 is 1, but you have a negative, so it's negative 1. So 2 to the negative 1, it will be negative 1/2. 2 to the, oh no, right. And 2 would be 2 minus 1 is 1, so it's 2, so it's negative 2. So you graph it as, normally at 1, you would go to 1, but 0 you go to 1, it becomes here. At 0, it go to negative 1/2, and at 2, it go to 2. So it will be a reflection of the 2 to the x function, b to the x function. What about e to the x plus 1? What kind of transformation do we have? It is only a up 1, right? So it is very easy to do. E to the x is like this. It's 0, 1, and then 1, 2.7, right? So up 1 means the whole thing just becomes 0, 2. And instead of 2.7, we would have 1, 3.7. 0, 2. And our new asymptote would be y equal to 1. Okay, so that's how we graph it.